Great. Well, thank you for that kind introduction and for the opportunity to speak to you all. As this is a joint work, let me just first say with a number of folks, and then I want to say more about Charles University. But these folks are all students or postdocs at Argonne over the years, and so part of this talk will be a sales pitch along those lines. But first, I was talking yesterday. Oh, the picture didn't fully load over here on the right, but I was talking yesterday with Professor Malik and with Jiri, and I had walked by Charles University, it turns out. And I see this because in June 2009, I took the photo on the left and the photo on the right. And the photo on the left is not very exciting, other than I think if you go, deep over here in this along this street, this is where the main campus of Charles University is. And then on the right would be the image that would have appeared on the right is a picture that you see once you've passed Charles University. So by virtue of having taken the first photo and the second photo, I believe I have walked by Charles University. And this was in 2009 before Zoom was even thought of. So I wanted to at least make that connection and say that I wish that we could all be in person, but I think it's fantastic that the SIAM chapter has this virtual seminar series. It's a way to stay connected around the world and has allowed us to, have talks and talk about mathematical research, even when we don't have to get on a plane and have jet lag. So let me just set up the problem that I would like to speak to you today. And this is about mathematical or numerical optimization. And I say nonlinear because we're talking about nonlinear functions. So the goal in optimization, just a quick review, is that we want to find some vector of parameters. That's always going to be X in my talk, from belonging some domain omega. And the domain is not going to be important, I think, for much of what I'm going to say, in order to improve some objective, which is always going to be the scalar valued function little f. So the problem is just to minimize this function f subject to X belonging to omega. And the thing about this problem is that unless maybe omega is very special. It could be a singleton, for example, just one single point in Rn. You're going to have to evaluate this function f at many of these parameters x in order to find a solution to this problem, let alone some approximate solution. So what I call a good x star. So throughout the talk, except where noted, I'm going to assume that the function f that we want to minimize is deterministic. It's going to be as smooth as I need, maybe to show a theorem or show a result. In some cases, I'll talk about when it's not so smooth. And I'm going to assume that this function f and really the domain omega captures a lot of information about the problem that you want to solve. So, some form of uncertainty that you want to capture would also be encapsulated in this function f and or in the constraints omega. So that's what I want to talk today. I'm going to talk about what's sometimes called black box optimization or derivative-free optimization. A slight variant of that is simulation-based optimization, where we're going to talk about optimizing objective functions f that are functions of simulation output, some of which may be black box or have no derivatives. I'll try to give an example and maybe make a connection to machine learning, since everyone keeps asking this question these days. And then I'll tell you a little bit about some more uncertainty things and how we can handle nonlinear robust optimization if we have time at the end. Okay, so this is the campus actually of Argonne National Laboratory, or at least what it looked like 20 years ago. And let's see, I'll point out a few different things. You see the large ring that's sitting up in the back over here. This is the advanced photon source. This is where hundreds of researchers come in any one week in order to do experiments associated typically with imaging, coherent diffractive imaging, and other hard X-ray science studies. The campus is much like a university, technical university, in that it has science departments and engineering departments and effectively every field of science and engineering. And a lot of the work that I'm going to talk about today is really born from some of the applications that come up in these sort of basic science things that are being studied at Argonne. The history of Argonne is certainly not as long as the history of Charles University. So 75 years you heard in the introduction, but there's some deep connections with math and with computation and with optimization that happens at the Argonne area. Karush of Karush-Kuhn-Tucker conditions, the KKT conditions, was, showed that result as part of his master's work actually at the University of Chicago. And the University of Chicago is what runs Argonne for the Department of Energy. So there's deep connections between U Chicago and Argonne. Davidon, sort of the D and DFP, sort of invented the first quasi-Newton method. He was a physicist at Argonne. And there's a rich story there that if you really want to look at Edward Snowden precursors many decades ago, there's excellent work on Davidon. So if you're interested in sort of side stories in mathematics, I certainly recommend looking up Davidon's story. And then here, of course, is Gibbons and Wilkinson at Argonne. We've got a number of programs at Argonne named after these two. I want to make it clear that we have folks from around the world at Argonne, and certainly if you're looking for postdoc opportunities or even summer student opportunities, maybe not for this year, but for coming years, I want to encourage you to reach out. There's a number of different ways that we can collaborate here, and we would love to see folks from Charles University and their collaborators work with us at Argonne. All right, so let's drill down into this problem a little bit more. So here is what I call simulation-based optimization. It's the same problem that we had before, but now this objective function, this little f, is defined by some mapping of simulation output. And my simulation output is always going to be this vector valued function s of x. It could be that the constraints that define your feasible region also depend on the simulation outputs over here. And I've put the emphasis here in red on the simulation outputs because these are going to be assumed to be computationally expensive, or expensive because you actually have to run a physical experiment to obtain the output of s of x given an input x. Typically, though, we assume that the simulation output is modeling some smooth process, so some process that's varying smoothly as I vary these parameters x. And derivative-free optimization is the setting when the derivatives, so I've written it here as the gradient with respect to x of the mapping s of x, that these derivatives are unavailable, or they're maybe prohibitively expensive to obtain for one reason or another. And then again, like I said, the expense of the simulation is sort of a key defining characteristic for research and optimization here, because normally in classical mathematical optimization, we're concerned with trying to compute our operations as efficiently as possible in order to show some kind of convergence result. And that means that we want to have the number of linear algebra operations that we are using to compute the next x to evaluate, let's say, to be as efficient or as small as possible. Here, because the evaluation of the simulation output is so expensive, this is really flipping that problem on its side, meaning that we have almost unbounded amount of time that we can use to determine what is the next x for evaluation relative to the cost of evaluating this s of x. And that might mean that the algorithms that we are considering here are a little bit different than those in classical optimization in some cases, because we can afford to do something more sophisticated between evaluations of this expensive simulation. All right, and these problems arise everywhere. So this is this is actually the hard X-ray ring that's at the synchrotron at the Advanced Photon Source at Argonne. Here is actually a quantum computer. Over here, all these stages are doing the cooling to get almost down to absolute zero. Over here, that's at Lawrence Berkeley National Lab. A lot of chemistry experiments happen at Argonne. You could imagine controlling a water resource system or calibrating some neuroscience model here. These are all areas where these expensive simulations might arise, or there might be data that you actually have to get from a physical experiment in order to get the output of this s of x. Okay, and computing is really a big driver for this, because people, now we can simulate more things with higher fidelity than we ever could imagine. So Argonne has a large history of having some of the largest supercomputers in the world. Back to 1953, here's the Avidac machine that you see. A machine that's still on the floor is this Theta machine, an Intel machine. And then an exascale machine is coming sometime next year called Aurora. And that means that, you know, people now want to do optimization. They want to do design, decision, and control on top of these simulations of physical processes. And this is where these things arise. So why is it the case that not having derivatives is going to be a problem for optimization? And, you know, from vector calculus, we know that conditions for optimality, you know, unconstrained optimization, are that the gradient of my objective function with respect to x disappears. If I have constraints, then, you know, you can look at the Lagrangian that I've written over here, the gradient plus some linear combination of the constraint gradients, that's going to vanish. And so right away, you see that if a necessary condition for optimality and optimization concerns these derivatives, then not having derivatives is going to, you know, cause me a problem algorithmically, because it's going to take out sort of the main thing that I need to have in order to recognize that I'm making progress. There are lots of ways, I should note, in order to get derivatives. And so I would be remiss to not talk about these. Algorithmic differentiation or automatic differentiation is a sophisticated way basically of doing the chain rule in order to get derivatives. And it tends to work with, you know, if you have source code for a particular simulation, then you can apply the chain rule to every line of that source code down to some intrinsic operations like cosine or sine or exponential or plus or times. And then you've pre-programmed up rules for what derivatives of those intrinsic operations are. And then you can apply the chain rule and back out the derivatives overall. The AD is also a key technology in machine learning. So back propagation has really fueled a lot of the advances for training methods in machine learning. And AD is the fundamental technology there. The reverse mode of AD is back propagation. The problems are, of course, is that, you know, if I have a physical process, I don't have something represented by source code that I can apply AD to, I'm not going to be able to do this. Or if I have proprietary source code or other problems for AD, then I'm not going to be able to apply it. Numerical differentiation is another alternative, right? So this is finite differences that I think most people know from numerical analysis. And, you know, a key concern with finite differences, of course, is that in order to do a full gradient approximation, I have to do, you know, order n, where n is the number of parameters, evaluations of that expensive simulation in order to get a single gradient approximation. And then I have to worry about the step size of the difference parameter, for example. All right, so let's talk a little bit about black box optimization, which is sort of the simplest form of derivative-free optimization. And here I have a nice example. So this is taken across Argonne. This is roughly the same time as that picture actually in Prague. So this is actually an early prototype of the Tesla Roadster, I don't know, 12 years ago or so, 13 years ago or so. And here they're testing particular, you know, features of this car. It's on rollers, as you can see. You can see you have an actual human who's running it through various drive cycles. And the, you know, parameters that you wanted to determine in order to look at the control process and in order to understand in what settings you're getting good performance or stated performance in terms of you know, mileage and other performance characteristics of this car, you see that a person is basically running a video game, right? And they are driving, they have their foot on the accelerator, you know, and ready to brake, exactly like the computer screen, that monitor in front of them is telling them to do. And then a number of gauges are obviously hooked up in order to look at battery life and other characteristics for use in some in optimization. So this is a physical experiment, right? There's no simulation, computer simulation or mathematical model that's describing all of the processes associated with this, the human with their foot on the pedal, the car's response, the knowledge of the drive cycle that's coming up ahead based on that computer screen. This is purely, you know, data driven. And that's what black box optimization is. If I have an optimization algorithm sitting over here and some black box simulator, the only information that the optimization algorithm can get is by just probing that oracle, right? So I send you a vector of parameter values x1, and I get back an f of x1 for that. So only through this sampling process do I have any information about what's happening in that simulator. So that's what a black box is. And I'll skip over the example, which relates to performance tuning of computer codes. But many of these kind of experiment-based optimization problems are exactly of this nature. I find out something about my objective function only by making a query to this black box. So some of the most basic algorithms to solve these problems are called direct search methods. And let me walk through a couple of simple ones. These are always going to be n equals 2D kind of examples for visualization. So I'm plotting my decision variables, my X and my Y that I want to optimize over in the horizontal and vertical directions. So first is pattern search. It starts by sitting at a particular point, and it's going to then evaluate perturbations of that point at a pattern. And the pattern that is being done here is to look at the cardinal directions, so north, south, east, and west. And it does then the evaluation of that black box function at each of those polling points. And it is asking the following question: yes or no, is my function evaluated at this poll step less than the function that I'm sitting at right now at this red point? And if the answer comes back yes, then I'm going to go and accept this point maybe, and move to the next point, and I'm going to repeat this process. And there are mechanisms for growing and shrinking the pole size. So obviously you see the steps get larger in that next iteration. I guess I accept down going south again, accept going south, accept going south. I see a rejection, and then I'm going to shrink my pole steps, it looks like, until I say yes. If I go to the east, I see again a reduction, and I can follow my nose in this way. So this is a pretty simplistic algorithm, but it has a very rich convergence theory that tells you even in certain classes of these algorithms can also converge to cases when you have non-smooth objectives, when the objectives may be non-differentiable. Another direct search method is the Nelder-Mead method, sometimes called the other simplex method or the Nelder-Mead simplex method. And it's going to probe the space in a similar way, except for it's going to use simplices rather than these polling patterns that we have on the left. So a simplex in 2 dimensions is just a triangle. I evaluate all of the vertices of that simplex, and then I go and find out which of these function values on these vertices is the worst. In this case, it's sitting over here in the corner. And now I'm going to have certain operations that I can do, like a reflection operation, where I reflect along the face that's defined by the remaining vertices in order to do my next evaluation. And then my operations here are again going to be determined precisely by questions such as this, which says, did I improve the point, yes or no? If I improve the point, then I have a new simplex maybe that I'm growing out or making larger. And so the various operations that the simplex method, again, is doing is based off of, if you want, the ordering of the function values on the vertices of these simplices. The key thing about these direct search methods, that's why they're called direct search methods, is they're not doing anything to exploit the properties of this function f, actually. So you can show that they converge. Eventually, they're going to find solutions, local solutions for large classes of problems, but they're not taking advantage of any of the information that we actually obtain along the way. And in particular, again, this is just an indicator, right? The operations are based off these indicators or these orderings of these vectors. What they're forgetting about is actually this missing dimension, right? This other dimension, which says, what are the function values that I'm getting out? And now what I've done is I've shown you now in 3D, I show you actually the function values. If I show the function values here and I tell you that I'm going to assume the function is smooth, I can already start to infer some behavior, right, about what this function might be doing. And this is what's missing from direct search methods and prompts us to think about model-based methods. We have this bank of data that was really expensive to obtain. It says, what are all the points that I've evaluated and their associated function values? And this bank is going to get larger and larger as I iterate, as my K grows. So I'd like to take advantage of this information as the optimization, progresses. And, so here's a growing bank. And of course, the way that we're going to do this is we're going to put a model over this data that we've obtained, the scattered data. So this is what a model-based trust region algorithm is doing. Rather than minimizing this expensive function f of x for which I don't have derivatives, I'm going to do the usual nonlinear optimization trick and put in some proxy or merit function over here. We're going to look at a quadratic, I guess, in the next few slides, this qk of x. And I want to minimize this quadratic locally. So this local region is just indicated by this bk, which is called a trust region and defined over here. So the idea is I've got function contours that are in the dashed lines sitting over here. I want to minimize this function, but I don't know what those contours look like. I just have information at, let's say, these 6 red dots that I've shown over here. With those 6 red dots alone, I can form a quadratic model. And what I'm going to do is solve this subproblem, right? This minimize the quadratic model locally, and in order to obtain, some new point that I'm going to then do the expensive evaluation on. And that's what a trust region method is doing. So the trust region is this local region that we are assuming that we trust the approximation of our surrogate of our qk to approximate this function f locally. And then we obtain our new point, our x plus, and we just, all the updates basically are formed by the following scalar quantity, this rho k, which is the ratio of the reduction that we saw moving from xk to x plus to the predicted reduction. So the reduction predicted by the quadratic surrogate. And so again, you can put any kind of model that you want. I've looked at radial basis functions. This is a quadratic, but you could do a linear model, you could do a cubic model, or things like this. They all tend to be based off some kind of Taylor-based approximation that says, my first order term in my quadratic needs to be roughly like the gradient locally at the center of the trust region, and maybe my second order information needs to roughly approximate the Hessian at that point. So that's what a trust region algorithm is. Now you iterate. So with that new information, you can accept the point based off of this ratio or reject it. If you accept it, then you can move. You're going to update your trust region, solve a new trust region subproblem. So you see that my contours of my models have changed in the interior of this trust region now. Or I can reject it and sort of shrink and grow the trust region as needed, just like the direct search methods. All right, so for black box algorithms, how do we obtain these models? Again, we don't have derivatives, so we're going to do it by interpolation. And I think you can see where this is going. In 2 dimensions, again, here are my points sitting in my input space. Circles are my points sitting in my output space. And I'm just going to ask for my quadratic model to agree with the function on some interpolation set, this calligraphic xk in this case. And I can do this now for polynomials, so in this case quadratics, depending on various conditions. And they all are related to how many points that I've previously evaluated. So if I've evaluated the number of points that is the cardinality of the basis of quadratics in n dimensions, written here, then I can do full quadratics. If I've got fewer than that number of points, I can do these kind of quasi-Newton type updates. So minimize the change in the curvature, or look for the flattest model, that quadratic model that interpolates the data. I can also, solve that interpolation in the least square sense if I have an overdetermined problem. So if I've got more than this number of points, I could maybe, minimize this the 2 norm of this system in order to obtain my interpolation coefficients. All right, so there's a lot of numerical analysis and approximation theory that's underlying this. A very cool math problem. And I'll just point one connection, that we all learn in numerical analysis that if we're in 1 dimension, so if n equals 1, then if we are given, p distinct points, then we can find a unique degree p minus 1 polynomial that interpolates those points. And that's very nice because it just says this is the only condition that we need, is that the interpolation points have to be distinct. For any dimension bigger than 1, that's not true. Distinctness is simply not alone. There's not a unique polynomial that will interpolate any kind of arbitrary scattered data. We need to have additional geometric conditions. And that was sort of alluded to on the previous slide. In particular, what it means is that a quadratic can't vanish on all of the points. So if there's a non-trivial quadratic that vanishes in all of the points, then you can imagine I have a null space in that sort of polynomial approximation problem. That would mean that I can't uniquely determine such a polynomial. And the image on the left is exactly just saying that. So, you know, if I've got 5 points living in 2 dimensions, the 6th point, in order to be able to have this uniqueness result, can't lie on these 2 blue lines. But because we work on a computer, we don't want to just not lie on those lines. We don't want to lie too close to those lines. We have to worry about conditioning and other problems. And that's what those contours are trying to say. So there's other kind of geometric conditions that show up anytime that we talk about these model-based methods, because we need to, you know, ensure that our approximation quality is such that that we've got good approximation in that trust region. I want to say one more thing about randomized algorithms before jumping into some more structured things and speeding up here. So randomized algorithms, these are algorithms where the random variables are generated by the method, not from the problem. So not stochastic optimization, although the stochastic gradient method is a randomized method, so there's some confusion there. And an example of that is this sort of random gradient or 2-point bandit method that Nesterov wrote an excellent paper on a few years ago now. And they operate as follows, you know, give me a starting point and some sequence of prescribed step sizes. Maybe, you know, the alpha k is just 1 over k, think of it that way. I generate a random direction, this UK direction. And now I'm going to make the following update, the following iteration. I take my previous point and I look at the difference of my function evaluated along that direction, some difference size h, from my function currently. So you can think of this as a directional derivative in the direction UK that's approximated by a finite difference with finite difference parameter h. That's giving me a scalar quantity over here. I take that directional derivative, I hit it by that same direction, I put a negative because I want to minimize, I dampen it, so by some step size alpha k, and I just accept this iteration. So unlike those other algorithms that I had on the previous slides, the model-based methods and the direct search methods, these randomized methods, you see at least this one, has no test that says, does the function value actually decrease, right? So it's certainly, it's possible that the function value increases in this iteration. Whereas the other methods sort of, that's one thing that they always want to have. They want to have a monotone sequence when considering these function values. Okay, so that's just a quick hint at randomized algorithms because I may want to say more about them later. All right, so but I talked about exploiting structure. I don't want to just do black box optimization. I want to solve optimization problems that have objective functions that are functions of black boxes. And these problems arise, you know, orders of magnitude more often in my experience than the pure black box ones. So a nice example of this is just simple calibration. I have some black box simulation S, and I want to calibrate it to some experimental data DI. And if I do that in the mean squared error sense, then I want to just minimize, my objective function becomes exactly as follows. So the key thing is the black box is the simulation output SI of x. It's not this quantity f of x. And for the next few minutes of this talk, I really want to talk about exploiting the fact that you know this knowledge of this structure in order to get better algorithms and better convergence and better empirical performance. And structure can show up in a whole bunch of ways. I can have some known function and some black box function. I can do robust optimization like we'll do maybe at the very end. It can show up in the constraints, so on and so forth. So how do we proceed for our model-based approach for these things? You know, again, we're assuming some kind of smoothness or regularity conditions on these black box simulation outputs, these SI of x's. In particular, I'm going to assume that they're continuously differentiable and that I can evaluate them. And I'm going to assume that the derivatives exist, the first order derivatives exist. But again, this is the part that I'm going to say is not available to the optimization algorithm. And then I'm going to do precisely the same thing I would do in the scalar value thing. I just do it now instead of just once for the objective function. I have to do it for all p of these simulation outputs. And the approximation bounds that we get by virtue of some of the theory hinted at in the previous slides, it's very similar to the kind of Taylor, multivariate Taylor bounds that you would get from just looking at derivative-based polynomials. So in particular, you want to have that your model of the simulation SI of x, that it agrees with SI of x, locally, so for all x in some delta neighborhood, by something that, is order delta squared. And that the gradient, even though it's not available, we assume it exists, the gradient of the model agrees with the gradient of this black box SI of x by something that grows as of order delta with that. So these are Taylor-like error bounds. You can just plug in the first order derivative based models over here for your model, these SI of x's, and this falls out naturally. You can also do this now for the derivative free setting. So how are we going to use this? So let's just have one slide on algebra. I'm going to, if I've got these sum of squared residuals Ri of x's, I'm going to come up with a model MRI for each of these Ri's. And this MR of I is going to basically interpolate at this reference point xk. It's going to have a first order term, so this gradient term, a second order term over here, so it's a quadratic model. And now what I'm going to do is I'm going to just compute what the derivatives would be of my objective function f of x. My derivative for this function that's written over here is just going to be a linear combination of the gradients of these Ri of x's. The gradients are unavailable, so I take the red bit and I replace it with the purple bit, which is just my approximation that's coming from this model. So everywhere you see an unknown gradient, it's a very simple recipe. You can just put in the gradient that you get from these approximation models. And the same thing, of course, can be true for the second derivative. We could do it for the third derivative and onward. I just have to stop at some point. And the key part of this is that you can see there's mathematical structure that's being exploited here in these approximations. And it's not that we are collapsing this Hessian into a single matrix. Really what we're taking into account is that that matrix is defined by the outer product of these first order derivatives of these component functions Ri of x, plus a linear combination of the second order terms of these Ri of x. And it's not just any linear combination, it's a linear combination that has Ri of x there, zero order information. So those are the function values that I assume that I do have, whereas the red stuff is stuff that I don't have. And so this is very, very nice because basically everything that's in black are things that I know and have in hand. The fact that it's a sum, the fact that it's an outer product, sum, and a particular set of weights that are occurring in that sum. These are all things that are known that I have for free, and everything that's in purple is sort of what I get from approximation. So now I can walk through error bounds through all of these things. I can have algorithms that take into account this sort of special structure and just follow my node.
Ano?
Yes.
Volno. Co pak?
Tady jsem ti tam nachystala, tak kdyby si chtěl pošplíchat ty boty.
So I was going to give an example over here for calibrating energy density functionals and talk a little bit about some stochastic methods. Okay, so maybe I will spend just a second on this because there's a lot of interest in stochastic gradient type methods, which are popular for training machine learning methods, and they also play a role in this derivative free case. So let me just quickly say something about these because they are in part an extension of the randomized methods that I hinted at a few slides ago. So the basic idea is that they are looking at functions of the form that you can think of just the average of a large collection of component functions, capital Fi of x. And so one example, again, is just the mismatch of my model and my data, or mismatch of my simulation and my data. And my simulation could just be an artificial neural network. So that's the think deep learning. Or it could be a black box. And what these methods do is they, on every iteration, they replace basically this function f with a function fb, which is just the batched view of that function. In particular, rather than evaluating all of these huge number of capital N FIs, they're only going to evaluate those functions that are in the current batch bk, and then take the average there. So they've replaced that function by this simpler to evaluate function by virtue of the batch size being much, much smaller than n. So the algorithm is as follows, similar before. You give me a starting point, a prescribed step sequence again in this simplest of algorithms. I generate maybe uniformly at random a batch from the integers 1 to capital N. And then I'm going to go compute a direction by looking at something like a gradient or average gradient based off of that batch. So when people talk about stochastic gradients, that's exactly what they're talking about. They're taking the gradients of these capital Fi of x's, but they're having a stochastically generated batch that they're going to use to determine the step. And then they just follow their nose. So they take the current point that you're sitting at, go in the negative direction of this approximate gradient by virtue of some alpha k. Okay, and rich history there. One quick illustration of what these things do. So suppose that I'm trying to fit some type of a trigonometric model to some data over here. And I've got 100 pieces of data. I'm only going to, at every iteration, use a batch size of size 2. So I'm going to grab 2 pieces of data, uniformly at random in every iteration from the blue points over here in order to determine my steps. So what you see then is that the function f has the contours sitting on the left, whereas if I just do a batch size of 2, and I guess in the first iteration I've grabbed the 7th and the 12th point in my batch, the algorithm is seeing just the view of the FB function. And the contours of FB function in this case look very different, obviously, than the contours that are sitting on the left. But if I take a step along the negative gradient with respect to FB, and then I truncate at some point, I get the new iteration point. I can go now iterate from there, right? So I go grab my next batch. This time I'm grabbing the 32nd point and the 77th point. I'm getting a direction now over here. It looks like these 2 batches agree, I would say, more, the FB contours on the right agree more than in the previous step, certainly, with the contours that I saw previously. I can take a step, again, new batch. It's going to push me in some other direction, and I can just iterate on this process. Catch up here. I can do this from many different starting points, and these algorithms, again, they can be shown under various circumstances to converge just based on this limited information, where rather than doing 100 of these data mismatch evaluations, I'm only doing 2 evaluations in every iteration. All right. The truth of the matter is, though, that these batch methods, they can be very, very poor in any case when n is not huge. And for most of the physics problems that we have over here, we tend to be data poor. We have a much smaller amount of data that we can evaluate, that we have for evaluate, experimental data, let's say, coming from some detector. And instead we have, we don't have simplistic neural network models. We have these, first principle based simulation type models that we're trying to calibrate. And the take home from many of these things that I want to sort of get at is simply that the stochastic methods over here, they perform poorly in this setting where n is small. So you have to do something more clever. And the thing that you do that is more clever is sort of this model-based approach that I've been showing previously. And the gains that you get are huge, I want to point out. So think of time as being what's happening here on the horizontal axis. Quality is on the vertical axis. I want to be as low as possible, as quickly as possible. And I want to point out that we have log scaling in the time axis. So these model-based methods, they are orders of magnitude faster than many of these sort of simplistic, bandit type methods. You've got to do more clever things in order to take advantage of the information and the structure, and that's really what's allowing you to solve problems quickly. All right. So just in a few minutes remaining, I'm going to skip over the lesson that says that you can do this for non-smooth optimization, and just talk a little bit about what do you want to do if you have some amount of uncertainty in your problem and what that looks like. And I want to come back to this idea of taking a small amount of points in order to solve an optimization problem, or calibrate a model, or train a machine learning model, and look at sort of training and testing error. And the training error, this is, you can think of this as your batch. This is what you have in hand. And the testing, think about that as your global population, how you actually want to perform well on. And if this is a cartoon, let's say, of my parameters x as a function of my error that I'm seeing, what I see is that I have a very sharp cusp sometimes in my training error and or in my testing error, which means that if I actually took the solution from just my training problem and evaluated on my testing, I would get relatively poor agreement because I see fast variation there. And this is a problem in these training processes for the generalizability of the solution. How well will your solution of your optimization problem or of your fitting problem work out of sample? So one way to do this is through robust optimization. And I want to spend a couple minutes on this nice little game over here, which is the following. So the function that I have in hand is this red function. And I'm going to design this blue function, and this blue function is going to be this psi of x function. And the psi of x function is defined in the following way. You give me an x, right? That's the input, the psi of x. And now an opponent is allowed to perturb that x by some uncertain variable, this variable u. But the opponent can't just do that in an unbounded sense. They can only make, let's say, size alpha perturbations of their thing. So you want to minimize this psi of x function. So you want to have this as be as small as possible, but your opponent is going to choose the u in order to maximize this. So this is sort of the worst case perturbation that you could see. You choose x, opponent says, I'm going to try to mess you up, and I'm going to go choose the u so that you do as poorly as possible. All right. Now, depending on what the size of this alpha is, I'm going to get different solution characteristics. And I want to come back to the example on the left and say that, if my alpha is of size 0.1, all that I'm doing is I'm sitting at a particular point and I'm saying by how much is the function changing a distance alpha away. So, and that's why my blue function, my dash line over here has the height it has, because, I get this sort of worst case behavior, a distance 0.1 away. If I change what my alpha is, the size of that uncertainty set, then suddenly the best value that I see, even at alpha equals 0.3, is going to be fundamentally different. It's going to be at this much broader valley that I have sitting over here on the left, that is going to have much better generalizability behavior, and or is going to perform much better in settings where I have some type of uncertainty that I want to optimize over. All right, and we can keep on doing this. A couple of notes. I have made the problem a lot harder mathematically by formulating it like in this way. So I've made it better for the engineers and scientists that are taking the solution, because I've robustified the solution and improved my generalizability. I've taken into account that I can't manufacture things perfectly, let's say. But what I've done now is I have a more complicated function that I need to optimize. And in particular, what you see is I now have points of non-differentiability in this psi function. And these points of non-differentiability, or even these flat regions that are associated with local maxima, that's going to cause additional challenges for optimization, both in theory and in practice. Okay. So there's no free lunch in that sense. But even when the function f over here doesn't admit full derivatives, you can do this. And I wanted to say is, such problems arise in many things. At Argonne, people are very interested in additive manufacturing. So, this is these kind of powder bed 3D printers where you want to craft things basically by having a laser that is generating a melt pool. And the issue with these manufacturing problems is that you don't just want to design it for the idealized situation. You want to know that by this manufacturing process, you can introduce small defects that are where the small is effectively that alpha. That small is within your control because it's a characteristic of either the printer or the material that you're working with. So when you want to design something that's going to go up in space, for example, you don't just want to optimize it and say, we assume that this 3D printed piece was designed perfectly. We want to take into account the fact that these 3D printers are imperfect, but that their imperfection is somehow bounded in a particular way. So that's where robust optimization can help. Water treatment is another example where different stages of a water. So this is an actual water treatment facility outside of Chicago, kind of close to Argonne. And what they are doing is they're taking out particulate material in the water supply, which is probably very important in a pandemic. As you might imagine, people are paying much more attention to this. And this is done through various stages, and each one of those stages has the potential to allow certain things past its stage. So when you want to optimize the placement of these systems, you need to take into account the fact that the particles that are coming through over here are not precisely from some known distribution, but that there are some error bars on that distribution that you can quantify in a way. So that's another robust optimization problem. So I want to skip some pretty pictures and just sort of end here. I'll give you a picture that says, like, look, even when I have these nice smooth problems on the left, if I now look at the robust problem on the right, clearly you can see regions of non-differentiability, all of these cusps that are appearing by virtue of the robust, by virtue of this robust optimization kind of formulation. Very cool things, you can look at these phase plots that I really like, which is looking at, the angle at which the opponent's solution is best. And, you can coordinate these with local maxima and with saddle points that are sitting over here on the left. But pretty pictures. Instead, I'll stop and conclude, and I'll say that we've been calling these algorithms gray box algorithms. And that's because they're designed to solve these optimization problems that have black box components, but are not purely black box optimization problems, because I know something. I know some mathematical, some algebraic, some analytic structure about the objective function or the way that my objective function depends on the parameters. And this is what we want to be able to exploit. These problems where derivatives are missing, we have these black box components. They show up in a variety of these design and engineering and calibration problems. And really, if you can take advantage of knowledge about how this arises, then you can exploit this in order to solve problems faster and more accurately. This algebraic structure, so this mathematical structure that we like to exploit, it comes in many forms. And this is sort of a key SIAM kind of a lesson, that it really involves a dialogue between mathematicians and with the domain scientists, the domain experts, in terms of what are the actual characteristics of the problem to try to elucidate this mathematical structure. So this is, mathematical modeling 101, and is a very time-intensive thing that, but very much worthwhile when it comes to actually solving real problems. And then some references just with collaborators. With that, I want to thank everyone for your attention. Thanks again to Jiri and the entire SIAM chapter at Charles and Professor Malik for the kind invitation. And I'm happy to talk not just now, but by email if there are any things that you want to follow up on. My webpage is listed on this slide as well. If you'd like to know anything about student opportunities or postdoc opportunities at Argonne, or we can provide other pointers or areas for collaboration, not just in optimization, but in applied mathematics more generally, then I'd love to talk about that. So thank you again.
Okay, so thank you very much for an amazing talk. And now here comes the time for questions. So is there anybody who would like to ask a question? So maybe I will start. I would like to ask if you were talking, or you were showing us the game at the end of your talk. Was it just some toy problem, or is it really motivated by some application?
Yeah, so it is very much motivated by applications, and so this game is a little bit different than when people talk about stochastic optimization. They are saying that uncertainty is coming from a distribution. Robust optimization says that the uncertainty is coming from the support of a distribution. And so there's no probability here. This is a completely deterministic formulation. It just says, I want to be safeguarded against every possible perturbation. And that shows up exactly in these material science applications where you want to account for the possibility of defects, not just in probability, but entirely. So you want to be able to say, I can manufacture this within plus or minus 1 nanometer. And now I need to understand that when I look at the performance characteristics of the thing I'm manufacturing, I need to account for the fact that I may have a plus or minus 1 nanometer manufacturing deviation on any of these things. So these are real systems, and they show up in the synthesis of fuel cells at Argonne, in this 3D printing problem, and then also in imaging of these crystallographic structures.
And how many dimensions have these actual problems? You showed us the game optimizing.
For the robust optimization, the dimension tends to be quite low, because these are much more challenging problems than just the standard simulation-based optimization. And what low means is typically the most common thing for real solutions is only a handful of parameters, so n equals 5. People are also solving problems in the sort of dozen of parameters, but they're not solving these robust optimization problems, at least nonlinear non-convex ones, in the hundreds of variables.
Okay, thank you. So are there any other questions?
So there's a question in chat asking, is there a way to qualify? So Andreas, I'm assuming that you don't want to unmute, but if you do, go ahead and ask. Is there a way to qualify the optimality of a given solution point in gray box methods, especially for constrained problems, like testing KKT conditions if derivatives are available? So, so this is a great question. For most of the convergence theory that we do in these black box and gray box, we start by assuming smoothness of the underlying quantities. And so we are appealing to the traditional KKT optimality conditions. What we don't get is we don't get exactly that, because we make errors in our derivative approximations of either the constraint functions or the objective function, or some cases both. And so it's those errors that lead to additional terms in the sort of KKT satisfaction properties, if you will. So that's the answer to that. Another question that I wanted to bring up, which may also be asking here, is what if I have a black box constraint? And black box constraints are very challenging, because in practice, a lot of these experimental systems are very noisy, and the constraint defines optimality, but you can get large jumps from moving from one area to another. And so this is where people are looking at chance constrained optimization and a whole bunch of other things to identify constraints that have behaviors that significantly change the optimality characteristics of a problem of a point locally. Does that help, Andreas?